Hello everyone. Just like Sandy just said, the topic is a little bit different. We are a software company that develop data processing solutions and artificial intelligence solutions for onboard computers. So this is not a work that we have done already. It's a work that is scheduled for next year via a GSTP contract, touch wood. And this is more or less what we are going to present. So first I will introduce what we are currently have and how we plan to apply this into the GR740. So yes, pre-existing work. So all our work is highly relying in parallelization, in multi-threading. And we have seen that if by using traditional multi-threading techniques, for example, when there are large volumes of data like SAR sensor data or images, they tend to saturate the computer when the volume of data is relatively large. This can cause all kinds of problems, from excessive power consumption to data losses and to massive delays in the processing of the data. However, there is a new technique, or relatively new technique. Actually, the processor in the operating system, the processors and the operating system have supported this for some time, but they haven't really come as popular as for the last 10 years since the financial industry started using them. So I'm referring to something called log-free programming. Log-free programming is a more granular way of managing multi-threading as opposed to traditional logs and mutex. In this case, you only handle condition race in very small section of the memory. And it's usually depicted like this. So it's a busy wait until you leave the computer in a consistent state. You leave the memory in a consistent state. So it's usually depicted as a plane trying to land. And the runway is busy, so it tries again later after doing a loop, etc. So this is the way to depict it usually. So it's basically, you try to write your piece of data to the memory until you leave the memory in a consistent state. So a constant busy trial. But these tend to be quite efficient. As a contradictory, they may sound the busy wait, and you can actually get rid of this saturation problem and get a more linear approach to data processing. This is not a simple thing. It's not just by replacing all the mutex by log-free atomic operations. It requires substantially sophisticated algorithms, but it can be achieved. It can be achieved. It's extremely difficult to program, but it can be achieved with enough skill in the field. Fortunately, the GR740 and previous version of the family have the possibility to run these atomic operations. Their internally low-level name is usually CAS, which refers to compare and swap. So we have this tool to perform this parallelization using log-free. We have tested it in the GR716. Obviously, the GR716 is a one core, so it doesn't make so much sense to use parallelization. No? But the goal of the exercise was to check if the context switch between threads using traditional mutex and log-free will yield better results, and it does. So if we tested a simple compression algorithm, compared traditional queues with our own, what we call internally the event loop, is our main API, and we managed to achieve a substantial performance improvement and a similar linear way to speed up with the increasing volumes of data. Like I said, it's a one core thing, so it's a experimental, really it's a theoretical effort, but the results show that with Artems, which is a real-time operating system we use, and with the Leon 3 architecture, the benefit of log-free are still there. Moreover, we show, some of you may have been to the Bremen Space Expo. There we had a demo together with Geisler showing a Reindl encryption algorithm running on the 716 quite efficiently. Besides this core API, the event loop, which commercially is called the Klepsydra SDK, the main product I'm going to show you here is the Klepsydra AI. We have other products for other sectors, but the main focus here is the Klepsydra AI. So how does Klepsydra AI work, and what has this to do with the parallelization, no? With the multi-threading programming? So usually to run AI, which are usually quite heavy algorithms, you need to perform some kind of parallelization in order to complete the calculation in a reasonable amount of time. The traditional approach is usually what is called parallelization, which basically consists of having a mathematical operation split in smaller identical bits, and each thread performing one part. Typical example is matrix multiplication. And the typical tool to do this is OpenMP. However, there is another approach to parallelize things, which is the so-called pipelining. It's not new. It's it was already available in the 80s, but it has been resuscitated in the community because it has increased the throughput substantially and also reduced power consumption. So it's it was quite a rediscovery to start using these technologies recently. So in Klepsydra, we have combined these two things. So this is our main novelty in terms of processing artificial intelligence, is a combination of these two concepts. So how do we combine them? First, for those who are not very familiar, an artificial intelligence algorithm looks a little bit like this line of layers. More or less, this is a simplified version for those that are a little bit more expert. But usually artificial intelligence means processing one layer or one operation in the artificial intelligence, followed by another one, and so on. There are variations with graphs, recurrent loops, etc. But the most simple case is like this. It's a simple line of layers, one after the other. So we decided to approach this in a two-dimensional multi-threading model. So we have two types of threads. The first one is the pipelining, where we break up the algorithms in different segments, each one of them running in a different thread. And the second part is the traditional parallelization that I just showed, where there are some AI layers, the so-called convolutional layers, that are particularly heavy in some cases. On those cases, it's much better to break it up in a traditional parallelization way. So we have these two dimensions. First, like horizontal, splitting the layers into in a pipeline, and then splitting within the layer into parallelization. So we have tested this and different setups, and we can see that it is consistent with what we could expect in theory. So you rely, like in the left hand, you rely heavily on pipelining. You usually get a very low CPU consumption and high throughput. So it's quite convenient in terms of processing with low power and a large throughput. This will be the case, for example, of first observation, where you're not so interested having a very low latency in terms of milliseconds or microseconds, but you're more interested in processing as many images as possible. No? And on the other hand, you have the opposite, which is the minimal pipelining and rely heavily on parallelization. And in this case, you can achieve substantially low latency, which is more interesting to the case of a lander, or setups where the real-time component of the AI is substantially more important. So this is in a nutshell what Klepsydra AI can do for you in terms of processing in CPUs. Okay, so this is the most important thing. Another important aspect here is because of the pipelining that it has been built and the nature of the software, how is it built, it's quite deterministic. It can be stopped pretty much at any time. Other more traditional AI solutions tend to be more monolithic, where once you enter an image for the AI, you just need to wait for the whole process to complete. With Klepsydra, you don't need to do that with this software. You can stop it after one layer, for example, no? Or part of a layer. So yes, this is a little bit of a summary. Klepsydra is more elastic compared to other tools like TensorFlow. You can process either more data or consume less power, etc. So there is a kind of a range of possibilities here. But this can be complicated to configure, determine which will be the best two-dimensional model to use. But I will show this in a second. The API is quite simple of Klepsydra. I don't want to entertain too much. It's a traditional API of AI applications. But what I was saying is the way to configure this thing. So for that, we have developed what we call the streaming distribution optimizer, which enables the configuration of the system in an automatic manner. Initially, it was called layer streaming distribution, which LSD, but the name may not be great for the community, so I changed it to streaming distribution optimizer, so SDO. And this works, it's a genetic algorithm. You run a few times in your target computer, so you have the GR740, you have your AI algorithm deployed there. You run it in you do a few dry runs, and after that, you let the genetic algorithm calculate the best possible configuration for you. If you are interested in CPU, it will give you one. If you're interested in latency, it will give you another one. So this is, in a nutshell, the software we have developed at Klepsydra. So what we exactly are going to do to adopt this to the GR740. So we call this the pattern project. The name is explained here. And the goal is to deploy this into the GR740 and the GR765. Using the Artemis 5 as operating system. There is an open question there whether we will use the POSIX extension or not. It's still under discussion whether this will be pre-qualified at some point or not. The development will be done probably in the GR765 using FPGAs, and then it will be validated in a space-qualified hardware. This is the project, roughly. So what things do we need to do to get there? First is the threading is really important for us, as you can see. And the current version of Klepsydra AI relies heavily on POSIX, so the pthread API. So if we finally decide that we are not going to count on the POSIX extension to be pre-qualified, we will need to develop our own threading abstraction element, which might be good because one of the things I learned recently about the Artemis software is that there are other APIs, internal APIs, that are faster than POSIX for multi-threading. I'll ask later as well about this. But in a nutshell, yes, we need to do an abstraction layer and enable this multi-threading framework to work transparently for us, no? So we can adapt to POSIX or not POSIX API, so we can have our own internal proprietary multi-threading API. But this is the part that is more or less straightforward. The part that is a little bit more complex is that our, like any other artificial intelligence inference engine, we have a mathematical backend underlying. We have our own mathematical backend. We have two, actually. One for what we call the full backend that supports non-quantized and quantized models. So that's when the data comes in flow 32 or in int 8, sorry, for example. Or we have a simpler quantified only backend that only support int 8 input data, vectors of this type of data. At the moment, we support this architecture, as you can see, ARM and x86. And in order to support Leon 4 and Leon 5, we need to translate our current usage of the mathematical operations supported by ARM and x86 into the vocabulary of Leon 4 and Leon 5. So this is one of probably the biggest effort. We also rely actually even in assembly code to perform some operations faster. We rely on the vectorization, so the SIMD, the Neon, all the FPU instruction sets of this ARM and x86. And this is the biggest effort is how to translate it exactly into the Leon 4 and Leon 5. This is probably the biggest effort we have to do for this project. And also, again, parallelization for the actual parallelization part. I explained that we need to do this for the pipelining using our own multi-threading framework. We will need to make the same change to our parallelization framework, which also rely on POSIX. So these two-dimensional threading models both rely on their own independent API, at the end relying on POSIX. So this is roughly the technical effort we're going to do. So the plan is first to do the Artemis 5 porting, so the multi-threading API, followed by the Leon 5 instruction set translation, and finally the validation. So this is our current plan. The goal of this project is to complete it in 12 months. It's quite ambitious, so we need to have a number of people working on this project in order to achieve this goal. And yeah, so this is more or less. After that, after we complete this product, there will be big benefit to it, no? It will be possible to use artificial intelligence on these processors, the GR740 and the GR765. The software itself is quite lightweight. It's only 4 megabytes. We did it on purpose so it can be uploaded potentially to existing missions. It's very deterministic, like I said. It can be stopped at any time, and it's highly optimized. So it will be the software will be developed, will be highly optimized to these processors. Therefore, we'll be able to run real artificial intelligence on board. No, this is the key. Operative word is real artificial intelligence. So, for whatever purpose, Klepsydra AI will be able to handle this. After we finish this project, there are some follow-ups we want to do. One of them is an in-orbit demonstration, possibly in the OPSAT onboard computer. This computer has this onboard computer has an FPGA where we could potentially program the GR765, so that will be an option. Another area of interest for us is the health monitoring of the onboard computer as well. So we can, in real time, with our software, we can switch from stop using one core if the core is showing some failures due to radiation, temporary failures. We can switch to the other cores, and when it's when the core is recovered, we can go back to this one. So this is all. Thank you very much. You have any questions?